In this problem, we are asked to consider an adiabatic turbine. We need to determine the amount of work delivered from this device per kilomole of a real gas that flows through the system. The equation of state that describes the PVT behavior of the gas is given. We are told that the gas at the outlet of the turbine is at 100 kilopascals and 300 Kelvin. Let's call this state 2. The inlet conditions are not specified. However, we are told that a small amount of gas is bled off through a throttling valve just before the inlet to the turbine, and the state of the gas at the outlet of this throttling valve, let's call it state 3, is measured, and this is at 650 Kelvin and 200 kilopascals. So this state is fully specified. State 2 is fully specified, but we do not know the state of the gas at the inlet of the turbine. We have a restriction in terms of the data that we have available, since the CP value of the gas is only available at 200 kilopascals. From our energy balance over the turbine, steady state, adiabatic, we should all realize that the work that we are interested in can be calculated by H2 minus H1. And that will give us an answer of work per kilomole of the gas. However, we do not have any information at this state of the gas. And when this question was set in the exam, most of the students spent lots of time and effort in trying to define the state of this gas, instead of stepping back and realizing that if I do an energy balance over my throttling valve, and by applying all our assumptions for a throttling valve, we can prove that H1 is equal to H3. Now, instead of trying to use this information to calculate the state, the temperature and the pressure at point 1, we can simply substitute H3 into our energy balance for the turbine. So now we can calculate the shaft work delivered per kilomole of gas by considering the change in state between state 2 and state 3. So in order to solve our problem, we need to calculate the change in enthalpy for a gas per kilomole as its state is changed from an initial condition at 200 kilopascals and 650 Kelvin to its final state at 100 kilopascals and 300 Kelvin. Our path is restricted by the information that is given. Since we only know the CP value at 200 kilopascals, we need to consider the change in temperature at the high pressure state of our gas. So this will be step 1, change in temperature while the pressure is constant at 200 kilopascals, and the final step will therefore take place at 300 Kelvin. Step 2 will be at 300 Kelvin, change in pressure from 200 to 100 kilopascals. So during the lectures on real gases, we derived this expression using our Maxwell and our fundamental equations to describe the change in enthalpy of a gas with a change in temperature and a change in pressure. On a side note, please note that this equation, for instance, is available on your data sheet. So if you use it as is, you do not have to derive it unless you are asked to derive it specifically. So in this case, we can just use the equation, apply it to calculate our change in enthalpy. Because of our restriction, we are going to calculate the change in temperature first. So step 1, apply CPDT, and that's quite an easy calculation. And now we know that whenever we have to use a temperature in this part of our evaluation, it needs to be 300 Kelvin. In order to evaluate this part of our equation, we need to write our equation of state such that the volume is the subject of the equation, because we are going to have to differentiate first to temperature and substitute the value for volume into that equation. So now we've differentiated the volume to temperature, and we have an expression for our volume as a function of temperature and pressure, which we can now substitute into our equation. So this part of the resultant equation is where I multiplied the slope with the temperature, and this is simply equal to volume. So now the equation that we finally get that we must integrate to find our change in enthalpy when the temperature is constant while the pressure is being changed from 200 to 100 kilopascals is simplified, because these two cancel out. I can group the terms together, and now your calculators can do it, but I will just show you that we can still do it by hand. The only tricky part is to remember that we now must substitute the temperature at which we are busy considering this change in state at constant temperature. So since we already changed the temperature from 650 to 300 Kelvin, it implies that in this last step that we are now busy calculating, the temperature that we must substitute in here must be equal to 300 Kelvin. After substitution of our parameters and the correct temperature value, we get a change in enthalpy due to the change in pressure of 1990. And if we add the values for the two steps, we can calculate the work that we can obtain from that turbine per kilomole of this non-ideal gas that flows through it. So I want to give you a challenge. So using exactly the same problem statement or the conditions of the gas, set up a solution for how you can in fact calculate the temperature as well as the pressure at the inlet to that turbine. I would love to hear from you. Remember, you've got two unknowns. How many equations would you need? How would they look? How would they be different, because we've got the restriction of the CP value of the gas only known at 200 kilopascals. Good luck.